Hello, good evening, all of you. I have already shared you the PDF of previous lecture, and you might have seen it, and also tried the problems that are given in the PDF file. Now, what we will do, we will continue with some of the more problems related to PDA. Now we have to design a PDA for well-formed parenthesis. Well-formed parenthesis, and let us design that PDA using both that is acceptance by final state and by empty stack, and we will simulate it for input. This is the input, this is the input, well formed parenthesis, this is the input, and at the same time show stack operations. So that we will try to do in this problem. Now, what do you mean by well-formed parenthesis? Actually, in arithmetic expression, we encounter the parenthesis, and the parentheses are written like this. For example, expression E is equal to A plus B into C divided by D minus F, something like that. So here this is called as parenthesis. So what is a well-formed parenthesis? So well-formed parenthesis means for opening parenthesis there should be closing parenthesis. That is the equal number of opening parenthesis and equal number of closing parenthesis. So now, so what is a language that it will contain? L is equal to. So for example, we have an expression E is equal to A plus B. So there is no parenthesis right now. So we have no parenthesis means null is also well-formed parenthesis. Then we may have one opening parenthesis, one closing parenthesis. So what will be that language? This will be opening parenthesis, this is closing parenthesis. Then we have two opening parentheses and two closing parentheses. So what are different combinations of that? So this will be the combination. This is one combination. Another combination could be this. This is also valid well-formed parenthesis in which two opening and two closing are there. Now, three opening and three closing. What will be the language? So this will be the language 1, 2, 3, 1, 2, 3. So this is well-formed. This is two opening, two closing with one opening, one closing. This is also valid. Now, this with this is also valid. Now, so these are things that are valid parentheses. So this is a part of the language. So now what logic you will apply? Now what logic you will apply so that you can come to know that it is a well-formed parenthesis. So
कौन दीदी?
So now, so what logic you will apply? So let us take, so whenever you get opening parenthesis, so for opening parenthesis, like this. So whatever opening parentheses are there, you push that on stack. So for that, push on stack. And whenever you get a closing parenthesis, then pop the stack. If top of stack contains opening parenthesis. So, and then again, if you get the opening parenthesis, then push it, then closing, you pop it. Okay. So that means these operations, push and pop will happen at any time. So there are no two separate states which will do push and another state which will do pop. So now let us do it with the one state. Okay. So let us have now Q0 state, which is a starting state. Now you come into this state, start. Now when you have the opening parenthesis and Z0 on stack, then push that opening parenthesis on the stack. When you have an opening parenthesis with opening parenthesis on top of stack, then also you push that opening parenthesis on stack. Now, when you get a closing parenthesis, that this is a closing parenthesis, and when you have opening parenthesis on stack, then pop it. Okay, that means you are doing that into the same state. And now when your input is finished, and that is you have a null as an input and Z0 on stack, that is stack is nothing, then keep the stack as it is and come to a Q2 state, which is the final state. Now let us try to simulate it with the stack operation. Show stack operation for, now our input is now for stack operation to be shown is this. Okay, so let us take that. So opening, closing, then opening and then closing. So how do you show the stack operation? So you show the stack operation like this. You have a state, then input, then stack, and then operation. What operation we are doing? The stack operation. Okay. So right now, initially we are into a state Q0. Input is the entire input, which is this is the entire input, and stack is Z0. Right now we have no operation. So now here opening parenthesis and Z0 on top of stack. So as per this, what we are doing, if opening parenthesis is there, this, then we are pushing that onto a stack. For opening parenthesis, let us push on stack. So we are into the same state Q0. Opening parenthesis is gone. So opening parenthesis, closing, closing, and this is a remaining input, and this goes on stack. So what is the operation? So this is a push opening parenthesis. So this operation we are doing. Now again we are into the q0 state with opening parenthesis. So we are into the same state q0. Opening parenthesis is again pushed on stack. So closing parenthesis, closing, opening, closing. So now we have on stack cc z0. So what is the operation? So this is again a push operation with this. Now it has now come into closing parenthesis. So what we are doing for closing parenthesis? So closing parenthesis, if the top of stack contains opening parenthesis, then pop it. Okay. So now here see, this is a closing parenthesis and top of stack contains opening parenthesis. Therefore, it is into the same state Q0. Input is consumed. So remaining input is this opening, closing, and this is popped. So remaining is CZ0. So now what we have done now, operation pop this. Okay, that is a pop operation, we have done it. Now again the input is closing parenthesis and top of stack contains opening parenthesis. So again we are into the same state Q0. So this is consumed. So remaining input is this, and stack contains Z0. So what operation we are doing here? We are again pop opening parenthesis. Now again opening parenthesis and into q0. So what we are doing onto the q0, when opening parenthesis is there, we are pushing onto stack. So now q0, so opening parenthesis is gone, remaining is closing, and stack becomes cz0. So it is push operation. Now again into q0 state, closing parenthesis, top of stack contains opening parenthesis. So it is q0 again. Input is now finished. It is a null input, and z0 on stack, and here it is a pop operation. Now we are into q0 state, and when null is the input and z0 in top of stack, then we are coming into a final state. Okay, so q2. So now let us see that. So we are coming into, sorry, q1 state, not let us make it a q1, that's better. Make it as q1. So q1 state, and null is the input, z0 on stack, and we are keeping the stack as it is. Keep stack. So it is just a peak operation that we are doing. So this is the stack operation for input this. Okay. Now let us show the simulation. Show the simulation for input. Let us take a different input, and the different input is this, and we have, let's say, a simulation for input which is not part of the well formed parenthesis. So now let us take this. Okay, so this is not well formed parenthesis, it is not well formed. So our PDA should reject it, should reject or not accept it. Okay, so now how will we show this? So we'll show like this. So delta, we are in q0 state, input is opening parenthesis, closing parenthesis, and then closing parenthesis, and stack contains z0. So now, so what we are doing, so we are right now in opening parenthesis and stack is z0. So what we are doing, we are pushing that onto a stack. So we are having the input, now remaining input is this, and stack is cz0. So now again in q0 state, now it is a closing parenthesis. So we are into q0 state, this is consumed, so remaining input is this, and stack is popped, so it is z0. Now we are into q0 state and we are getting closing parenthesis and z0 on stack. Okay, so is there a move for that? So see here, so we don't have any move, which represents the closing parenthesis and z0 on stack. Okay, so we have a closing parenthesis with opening parenthesis on stack, then go to the Q1 state. No, sorry, remain into the same state and pop it. Okay, so now here we don't have any move further, any move further. So here PDA stops, PDA stops. And once PDA stops, now it is stopping into Q0 state, which is not final. Q0 state is not final, not final. And also stack is not empty. Stack is not empty. Therefore, the string opening parenthesis this is not accepted. Okay. Now let us design the same PDA using empty stack. Now design using empty stack. So how will you design it? Empty stack, here we should not have this move. Now also in this case, what we are doing, we are also having a null as an input. So here, what if in Q0 state we get a null as an input? Then also we need to have one move which represents for null input. So when we get a null as an input and Z0 on stack, then we come to Z0. So what this is representing? So this is representing a null string. Okay, getting a point? Now let us try to design using empty stack. So for that, again the same Q0 state, it is a start state. And here we have a opening parenthesis Z0 on stack. We are pushing that into on stack. Opening parenthesis on top of stack, then we are pushing it. And again now we have a closing parenthesis and we have a opening parenthesis on top of stack, then we are popping it. And now here we will add one more move, that is when null is the input and Z0 on stack, then pop it. Okay, so here with one state only we could achieve the PDA using empty stack. Okay, so this is a PDA using empty stack. Now let us all of you can show the simulation here. Simulate this PDA for, let us take this input. Okay, for this input, try to simulate the PDA. All of you try in your notebook. I am waiting for 5 minutes. Have you done? Utkarsha, Sanskriti, have you all done? Now let us see the next problem. Now the next problem is design PDA to accept the language in which the number of A's and number of B's are equal, and we have to accept it by final state. And the W belongs that it is a zero or more combination of AB star. So now which will be the language of this L will be equal to? So if number of A's and number of B's are equal in the string of A's and B's, so null in which 0 A's are there and 0 B's are there, that is nothing. So that is also equal number of A's and equal number of B's. We have a string AB, 1A, 1B, BA, also valid string 1B, 1A. We cannot have three length string because in which one will be greater than another. So we will have now four length strings like AA, BB, it's a valid string. AB, ABB is also valid. Another string will be A, BBA is also valid. Another will be B, BAA is also valid. Another is B, AAB, and so forth. So these are valid strings. Now what logic you will apply? Now let us take a string and we will try to do it with the stack. So let us take a string that S is equal to that it belongs. Let us take W, sorry, the word W that belongs to this language. So W is equal to A, B, B, A, A, B. So it is a valid string. It contains three A's and three B's. So what logic we will apply? So right now we have a stack. Initially Z0 is on stack. So we now reading the input from A. So when I see A and nothing on stack, let us push it. So A goes on stack. Now my next input is B. So when I see B and I see the different top of stack. So number one, I could see both the things. That is empty stack I can see. Second thing, I can see the same symbols That is the input and top of stack are same. That is input is equal to top of stack. Or I could see different symbols. That is, in this case, input is not equal to top of stack. So now here in this case, when input is B, in this case input is B and top of stack is A. So that means they are different. So when they are different symbols, then what I'll do, I'll pop it. That is matching. And when I see the same symbols, then I'll push it. Okay, so let us do that operation. So now I see B as an input and A is on stack. So my stack will become now Z0 because A will be now pushed, popped from stack. Now my next input is B. So when my input is B and nothing on stack, that is the empty stack is there, then we will push it. So now B goes on stack. Now my next input is A. So now input is A and stack is B. That means different symbols. So here this will now B will be popped. Again Z0 will be there on stack. Now my next input is A. So A goes on stack and my next input is B. So A for that input A will be popped. So Z0 on stack. Now my input is finished, that is null, and stack is empty, that is Z0. So I'll go to final state. That is accepting the language. So now let us design this PDA. So we have now Q0 state. So start it. So when I see A on stack, when I see A as an input and Z0 on stack, that is empty stack, then I'll push it. When I see B as an input and Z0 on stack, then also push it. When I see A as an input and A is on stack, that is same symbol. Same symbols are there and I'll push that on stack. When I see B as an input and B is on stack, then also push it. Okay, so these are push operations. Push operations. Okay, and now when I'll do pop, pop will be done when I see different symbols. That is when A is the input and B is on stack, then pop it. Or when B is the input, A is on stack, then pop it. And when to stop it? So stop it when you come to, when you have now null as an input and Z0 on stack, then keep the stack as it is. So this is a PDA which will recognize equal number of A's and B's. Okay. Now let us try to simulate it. Simulate or show stack operation. Stack operation for. Let us show the stack operation. A, B, A, B, B. So here now equal number of A's and equal number of B's. So now let us show the stack operation. So how do you show it? So you have a state, then input, stack, and operation. So you are in the state Q0. Input is A, B, A, B, B, and stack initially is Z0. So now here Q0, A is the input, empty stack, that is Z0 on stack. So what we do, we push it. So remaining input is A, B, A, B, B. A goes on stack. So here push A. Okay, so this operation is happening. Now we have input A and A is on stack. So when similar elements is there, what we do? We do push. So Q0, A is consumed. So remaining input is B, A, B, B. So stack is now A, A, Z0. So again, our operation is push A. Why? Same element. Same element, that is input, is same as top of stack. Here why push A? Because it is empty stack. That's why we pushed it. Now we have input is B. So Q0, B is consumed and top of stack is, both are different. B and A are different. So what we'll do, we will pop it. So remaining input is A, B, B. So A will be popped. So A Z0 will be on stack. So our operation is pop A. Why pop A? Because input is not equal to top of stack. Now we have A as an input, A on top of stack. So what we will do, we will push it because same element. So Q0, A is consumed. So BB on stack. So BB remaining input, stack is AA Z0. And here what is operation? Operation is push A. Why? Because input is same as top of stack. Now B is the input, A is on stack. So both are different. So pop it. So Q0, remaining input is B, pop A Z0. So our operation is pop A. Then again Q0, B is the input. So Q0, B input is consumed, null, and A is popped from stack Z0. So our operation is pop. Now when null is the input and Z0 on stack, so we come to Q1 state, null Z0 and keep the stack, keep stack, or it is a peak operation. Okay, and this is acceptance of language, acceptance by final state. Okay, so this is how you can show the, you can design this PDA for equal number of A's and B's. So this has come for 6 marks. So for these 6 marks, it is sufficient. That is, you show this PDA, you may explain the logic in a short, because when you explain the logic in a paper, it means that you know it. And it is a good practice to impress the examiner. So you have a, if you have a habit of solving this problem, then you will not take too much time to solve it. Now, can you design a PDA? Design PDA for number of A's should be greater than number of B's. Number of A's must be greater than number of B's.
Yeah.
I'll wait for 5 minutes. You can unmute yourself and you can tell the logic. Can anyone? Who is topper in your class? Who is coordinator? Sanskruti? Who is topper? No one is there who can try? You can unmute yourself and tell the logic. Okay. So how you can do this? Now number of A's to be greater than number of B's. So what will be your language? So your language will be minimum language will be A. कारण A हा greater है. B नहीं है, B शून्य है, A एक वेळा है. Another AB cannot be part of this language, BA cannot be part of this language because they are equal. While as AAB could be part of this language, ABA could be part of this, or BAA could also part of this. याच्यामध्ये number of A's greater आहे. Now another is in which 3 A's and 2 B's or 3 A's and 1 B. That is, for example, AAAB is a part of this language. ABAA is a part of this. AABA or BAAA, so and so forth. So this is a part of this language. So how will you design this PDA? So what was acceptance state? So when you have a null as an input and Z0 on stack, you are going on to the Q1 state. So here only one change will be there, that is when input is finished and A is on stack remaining, still remaining, then we have it is a accepted. That means there are more A's. So what will be the PDF then? Start state. So when you have A as an input, Z0 on stack, then push that on stack. A is input, A is on stack, then push it. B is input, Z0 on stack, push it. And B is input, B is on stack, then also push it. So these are all push operations. Push operations for what? For number one, empty stack साठी हे push होते, and also when input is same as top of stack. So these are the push operations. Now we have a pop operation. So when we do a pop operation is done when we have a different input and top of stack. That is when A is the input, B is on stack, we pop it. B is the input, A is on stack, then pop it. So what are these operations? This is a pop operation. Pop operations when input is not equal to top of stack. Now we have to go to a final state. So when we will go to a final state Q1, when our input is finished and still some A is remaining on stack, indicating that A are more, then we keep the stack as it is and we go to the final state. So this is the acceptance of more number of A's in the string. If we want to have more number of B's in the string, then our condition will have now for more number of B's, for more B's, our condition will be null is the input, B is on stack, then keep the stack. So this is for more number of B's. So this is how you can design the PDA for number of A's are to be equal to number of B's or number of A's to be greater than number of B's. Now let us come to a theoretical topic. that is comparison between finite automata and push down automata. So that can be compared on various parameters. So the first parameter is external memory. So for external memory, since finite automata does not have a memory, okay, so it doesn't have memory, so it is none. While as the push down automata has the external memory stack. Okay, so finite automata only has finite number of states or finite memory. Okay, so it has a finite memory, while as the push down automata has an infinite memory or unbounded stack. So that memory is last in first out memory. If you see computational power of finite automata is less powerful, while as that of PDA is more powerful. Why it is? Because it only accepts the regular language, while as it accepts the context free language, okay, CFL. So that's why it is more powerful. Now, as told, it is accept regular languages and it accepts the CFLs. So which are that language? It is called type 2 language in the Chomsky hierarchy, and regular language is type 3 in the Chomsky hierarchy. How do you represent it? FA is represented by phi tuple. So what are that phi tuple? That phi tuple are Q sigma delta Q0 F. While as this is represented as 7 tuple, so what are that 7 tuples? Q sigma tau delta Q0 Z0 F. Okay, so these are the 7 tuples. So these 7 tuples includes the stack alphabet and initial stack symbol. So these two extra things are there in the definition. Transition function. So how transition function is written in FA? It is delta QA goes to a new state Q dash, while as here delta QAX goes to Q dash gamma. So here in this, it is a state, it is an input, it is an input, it is a stack. So that extra things are there. What are the example language that it can accept? So it can accept any string of A's and B's, okay, like A union B star, and it can do matching parenthesis, or it can do equal number of A's and B's, like A raised to n, B raised to n. It can also do palindromes. So it can accept the even palindromes. What is the practical use of it? It is used in lexical analysis, finite automata, while as PDA is used in syntax analysis and parsing. So typically they are used for tokenization, that is creating the tokens, and at the same time for pattern matching using regular expression. While as in PDA is used for checking the structure of the code, and it is used in compilers. What do you mean by syntax analysis? So typically in a programming language, if you write any error is there, then it gives the syntax error. So what is that syntax error generated? So this syntax error is generated using, or it is accessed using PDA, push down automata. For example, you have in a C program. In a C program, you have for loop for I equal to 0, I less than n, I plus plus. So this is a valid syntax. But if you write invalid syntax, so that is you write for I equal to 0, and you don't write directly write I plus plus. So no, don't write anything in between. Then it gives this as a syntax error. So this syntax error is done using pattern matching. So it tries to match the pattern for loop that first has to be initialization, then termination condition, and then increment decrement. But it is not matching with this. Therefore, that gives the syntax error. So what are the types of finite automata? So we have two types of finite automata. One is DFA and another is NFA. And if we see their power, then DFA is equally powerful with NFA. So NFA can be converted to an equivalent DFA. And so in this case, you say that DFA is equal to NFA. That is equally powerful. But here NPDA is strictly more powerful than DPDA. Why? Because NPDA is more powerful than DPDA. Why? Because NPDA can accept or can be used to accept palindrome, while it is not possible with the DPDA. So NPDA is more powerful than DPDA. Do you have any doubt? Now let us come to next topic, conversion of CFG to PDA. That is context free grammar to PDA. So what is a context free grammar? All of you know that. Let's say I want to write the context free grammar for palindromes. So how do you write it, that CFG? So let's say we have a language W belongs to AB star, and we want to write for CFG for palindromes. So how do you write that CFG? So you write S gives ASA or BSB or null. So this is a CFG for palindromes. Now this CFG, can we convert CFG to PDA? So this is a method. How to convert the CFG to PDA? So here the conversion typically results in a non-deterministic push-down automata, which is NPDA. So this PDA will always be NPDA. Conversion will always be NPDA. It will not be DPDA. It simulates the leftmost derivation of the context-free grammar. All of you know what is the leftmost derivation? In a parse tree, you have seen leftmost derivation and rightmost derivation. So when you have a grammar, let's say E gives E plus E or E into E or A or B, then every time if you replace the leftmost non-terminal with its production, then it is called leftmost derivation. And if you all the time replace the rightmost non-terminal with its production, then it is called rightmost derivation. So what this conversion is always leftmost derivation. The PDA accepts the input string by empty stack or by final state. We can have both conversion. And the transition function is constructed with three main types of rules for state. So what is the first rule? So first rule is a initialization rule, or called as a push start symbol. So what we do? So we, for this transition delta Q0 E Z0, we will have this push, that is we will push the push start symbol on stack. Okay, then we have the next rule that is called as a derivation or expansion rule. So this rule is applicable for non-terminals. So this is when a non-terminal A belongs to V, that is set of non-terminals, is on top of stack. Then what we do? Then we remove that non-terminal from stack and we replace it with its productions. Okay. So what we are doing here? Remove non-terminal from top of stack and push its productions. Now the last rule, that is called a matching rule, that is called as a consume terminal. So when the we have a terminal symbol on top of stack and the input is also terminal, then what we do? We pop the terminal symbol from top of stack. So that means what is the rule? So if input is terminal symbol and top of stack is also terminal symbol, then pop it, then pop the stack. Okay, so these rules to be applied for conversion of CFG to PDA. Now let us do with the example. So this example has come in university exam. So here design push down automata to recognize the language generated by the following grammar. And the grammar is S plus S, S into S, this is into, or 4 or 2. And we have to do this, we have to simulate it for the input string 2 plus 2 into 4. So let us see how we design it. So what is our first step? Our first step is push start symbol on stack. Okay, so here, so we are into Q0 state. This is a start state. So from start state we are going to a Q1 state. Okay, by pushing start state plus start symbol on stack. So when null is the input and Z0 on stack, then push S on stack. S is a start symbol. So this S means is a start of grammar S. If we would have been this kind of a grammar, like E gives E plus E or E into E or 4 or 2, then we would have pushed E on top of stack. Now we have various now operations like S gives S plus S. So what to do for now the production S gives S plus S? So what to do? How to convert that into PDA? So as I told you that this to be done with the matching of the second rule. So what is the second rule? Second rule says that when we have a non-terminal, then we have to remove the non-terminal from top of stack and push its production. So what we have to do now? Now here we have S on top of stack. So when null is the input and S is on top of stack, then push its production, which is S plus S on top of stack. Now what to do for this production? S gives S into S. So same thing to be done. So when null is the input, S is on stack, then push S into S on stack. And now we have one more production now, s gives 4 and s gives 2. So what to do for this? S gives 4 and s gives 2. So now s gives 4 means it's a terminal symbol. It is a terminal symbol. While as this s plus s is a non-terminal. So now when I have a 4 as an input and 4 is on stack, then pop it. And when 2 is the input, 2 is on stack, then pop it. Similarly, on stack, we also have plus as also the on stack and star is also on stack. So plus and star are also terminal symbols. Terminal symbols. And we have to consume the terminal symbols. So how to consume the terminal symbols? So when we have plus as an input and plus on stack, then pop it. When star is an input and star is on stack, then pop it. And when to terminate it? So go to the terminal, that is Q2 is a final state. When null is an input and Z0 only remains on stack, then go to the final state. So this is our final PDA. Now you can write this PDA. Now write this PDA as 7 tuple. So how it will be written? So it is written as 7 tuple Q sigma tau delta Q0 Z0 and F. So what is our Q? Which are various states in that PDA? So we have Q0, Q1, Q2. These 3 states are there. So that is a part of PDA. Which are the input symbols? Sigma. Input symbols are, see here. Input symbols are all the terminal symbols are input symbols. So we have 4, 2, plus, multiplication. See now in this case input. So we are giving the input this. See, this is the input. So 2 plus 2 into 4. So input contains 2, it contains plus, it contains star. It doesn't contain S. S is not input. S is the non-terminal. So terminal symbols are input. And union null. Null is also part of input as an end of string. Now tau is the set of stack symbols. So which are going into stack? So S is going on stack, plus is going on stack, star is also going on stack, 4 is going on stack, 2 is going on stack. Okay, so these are the stack symbols. So stack symbols are S, then who is going in stack? 4 is also going in stack, 2 is also going in stack. This also we need to add for 4 and 2. That is for S gives 4, what we have to do. So when this also to be added here, when null is an input and S is on stack, then push 4, that is remove S and push 4, and also add when null is an input, S is on stack, then also push 2 on stack. Okay, so these also to be added in this Q1 state, because it is also part of production. That is S gives 4. So for this we added, that is null as an input, S is on stack, push 4 on stack, and for this we added null is an input, S is on stack, push 2 on stack. Okay, so stack symbols also contain S, 4, 2. It also contains plus, it also contains multiplication, and it also contains union Z0, which is the start symbol. Now delta. So what will be the delta? So delta is Q cross sigma cross tau gives Q cross tau. Okay, so let us write down all these uh, part of your production transition function. So you can write with the help of transition function delta like this. So we have a production, grammar production, and here transition function. Transition function. So which are the productions we have? So we have these productions. S gives S plus S. So for that, which transition function we added? See here, for S gives S plus S, we added the transition function, that is delta Q1. So here transition function is delta Q1, null is the input, and null is the input and S is on stack. S is on stack, then it gives Q1 S plus S. Q1 S plus S on stack. Now we have another production, S gives S into S. For that we added a transition function delta Q1 null S gives Q1 S into S. We have one more production. So see here, the production is S gives 4 and S gives 2. S gives 4. So for that we have added projection delta Q1 null S gives Q1 4 on stack. And S gives 2, we have added this transition function delta Q1 null is the input, S is on stack, then Q1 2. Okay. Similarly, more transition functions are also there. So see, for example, this transition function that when null is input Z0 on stack, that is Q0. So this is the basic transition, some other transition functions required. Delta Q0, null is the input and Z0 on stack. Then we are going into Q1 state by pushing S on stack. Similarly, now when delta, we are into Q1 state, null is the input and Z0 on stack, then we are coming to Q2 state, S on stack. So these two extra transition functions are there, and along with we have a pop function, that is delta Q1, 4 is the input and 4 is on stack, then we pop it, that is Q1 null, and delta Q1, 2 is the input, 2 is on stack, then we pop it. So these transition functions are there into this PDA. Okay. Now let us simulate or show stack operations. Stack operations for, now which input is there? Input is 2 plus 2 into 4. Input is 2 plus 2 into 4. Okay. So now here we are in state, then input, then stack, and finally operation. So we are right now in the state Q0. our input is 2 plus 2 into 4 and stack initially is Z0. Now this is NPDA, non-deterministic push down automata. So it is not necessary that every time we will consume the input. So now we will now do the operation on null input. So we are now into Q1 state and input will remain the same. That is, we are not actually consuming the input, but we are reading the null input. So what is goes on stack? SZ0. So which operation we are doing? We are doing push operation. And what is the input? Input is null. Now Q1 input is same, that is 2 plus 2 into 4, same input. Now S is on top of stack. Also for null input, what we will do, we will add its production. So S is popped from stack and its production is added. So that is S plus S Z0. And here what we are doing, we are push. So we are doing push, which production S gives, S plus S productions we are pushed onto stack. Now this S is there, so we are into Q1 state and we will replace by its production. So now it is same input 2 plus 2 into 4. Now S is replaced with its production, that is S is consumed and it is replaced with 2. 2 plus S Z0. So here what operation we are doing? So we are popping pop S and push S gives 2. So that 2 goes on stack. Now we are in Q1 state. Now this input and this top of stack is matching. So do the now input reading and popping the stack. So now input is consumed. So plus 2 into 4 and 2 is gone. Remaining is plus S Z0. So what here operation is done, that input is same as top of stack. Therefore pop top of stack and consume input. Now again plus is there and it is matching with top of stack plus, so consume it. So Q1 plus is consumed, so remaining input is 2 into 4 and remaining is now SZ0. So now same thing, it is input is same as top of stack. Now this top of stack is S and input is 2, so not matching. So if it is not matching, then add the production of S. So this is Q1. Now here input is not consumed, 2 into 4 and its production is added, S into S Z0. So what we have done here, pop S and push its production, S gives S into S. So this is pushed on stack. Now this S is not matching with input, so its production will be pushed again. So Q1 2 into 4, S is now converted. So which operation? So 2 into S Z0. So which operation is done? That S gives 2 is pushed onto stack. Now this 2 is matching with this 2, therefore consume it. So therefore Q1 remaining input is star 4 and remaining stack is star S Z0. Okay, so here input is same as top of stack, therefore consume. Now star is matching with this star, therefore consume it. So Q1 4 S Z0 and input is same as top of stack. Now 4 is not matching with S, so replace S with its production. Okay, so let us replace S by its production. So that is Q1, remaining input is 4 and S gives 4 Z0, that production is added. So which production is used? S gives 4 is pushed on stack. And now this 4 is matching with this 4, therefore do pop operation. Therefore Q1 null is the input and remaining is Z0 on stack, and it is popped. Pop operation is done. Why? Because input is same as top of stack. Now you have Q1 null input Z0 on stack, so you come to Q2 state, which is the final state. Do you see? So here you come to Q2 state by on null input and Z0 on stack. So it comes to Q2 state, null is the input and Z0 on stack, and stack operation is keep the stack. And this is acceptance of the language. So this is how you have to convert the given CFG into PDA. So this is for 8 marks. So it is expected to write this much. First you design the PDA using diagram. Then you write its 7 tuple, that is write all its productions properly. So these productions, and do simulation showing the stack operations. All right. Any doubt? Actually, conversion of CFG to PDA is a mechanical process. तो हमें ऐसे ही करना है उसको. See, there is no logic actually into this. What we have to do कि अगर हमारा production है, so we have to push that production on stack. And when the input is matching with top of stack, then pop from stack. That's it is. So that is way you have to design the push down automata. Now let us see the next problem. Construct PDA equivalent to following CFG. So which are the productions? So x gives 0, or x gives 0x, or x gives 1xx, or x gives xx1, or x gives x1x. So these are the CFG. Now what is the process? So very simple process. You start with Q0 state. Start. Now first step is push the start symbol. So how do you push it? So when you have a null as an input, Z0 on stack, then push the stack initial start symbol on stack, which is XZ0. Sorry, here Z0 is also there. Now come to Q1 state. Now in this Q1 state, we will do push operation and pop operations. So when to do push operation? When stack is not matching with input. And when to do a pop operation? When input is matching with stack. So now here when null is the input and x is on stack, then push its production. So for x gives 0, that is for this production, then 0 is pushed onto stack. Now for second production, this is first production, second production, third, fourth, fifth production. So this is for first production. Now for second production, when null is the input, x is on stack, then push 0x on stack. For third production, when null is input, x is on stack, then push 1xx on stack. When null is input, x is on stack. For fourth production, put xx1 on stack. And finally, for the fifth production, when null is input, x is on stack, then push x1x on stack. So these are all push operations. Push operations for all productions. Now, when to do pop now? So these are pop operations. When, which are the terminal symbols? 0 is a terminal symbol and 1 is terminal symbol in our case. So when 0 is the input and 0 is on stack, then pop it. And when 1 is the input, 1 is on stack, then pop it. So these are pop operations. Pop operations. When to do pop operations? When terminal symbol, terminal input symbol is matching with top of stack, then do pop operations. So we have done this top pop operation. Now from here we will go to the final state. So when input is finished, that is null is input and Z0 on stack, then we come to Q2 state, which is the final state. All right. So this is the PDA diagrammatically. Now write this PDA as 7 tuple. Okay, so all of you write it. Okay, I shorten it. Okay, all of you, I give 5 minutes to you. All of you write in your notebook. Are you all trying? Friends, are you drawing it? Now try to simulate it. Okay, you might have written 7 tuple of it. Now try to simulate it. Simulate it for input 1 0 0. Let us simulate it for input 1 0 0. So how will you simulate it? Let us show with the stack operations. You can do with the with stack operations. So you have a state, input, stack, and finally operations. So you are into a state Q0, input is 1 0 0, stack is Z0. So stack is not matching with input. Therefore, what we have to do? We have to do a push operation. So in the Q0, we have only one push operation, that is pushing the start symbol of the grammar. So we are into the Q1 state, input is 1 0 0, and we are pushing that is XZ0 goes on stack. So push start symbol of CFG grammar. Now again 1 is not matching with X, so we have to push its production. So Q1, so which production will give 1 at the first? Do you see now which production can give 1 at the start? So you see that this third number production can give you the 1 on start. So we will push that production on stack. So now 1 0 0. So we will push 1 XX. That is X is removed, Z0. So what we are doing? We are push production. Which production? X gives 1XX is pushed onto stack. Now you see 1 is matching with 1. Therefore, if it is matching, then what we do? We do a pop operation. So that is, we are into Q1 state, pop operation. So remaining input is 0 0. 1 is consumed, remaining is XX, Z0. So it is a pop operation. Why it is a pop? Because input is same as top of stack. Therefore pop. Now, now 0 is not matching with X, therefore we have to do push operation. So which production to be pushed onto stack so that we can get 0 at the start? So see here, the production that we can push it, X gives 0. That production we can push it. So let us push that production. So we are into Q1, 0, 0 input. So X gives 0, X, Z, 0. So it is a push. So which push operation gives? X gives 0. That production is pushed onto stack. Now this 0 is matching with this 0. Okay. Similarly, so once it is matching, we will do pop. So we are in Q1, input is consumed, so remaining input is 0. This stack is popped, remaining is X, Z, 0, and it is pop. Why pop? Because input is same as top of stack. Now X is not matching with 0, so we need to push X production. So which X production will give 0 us? That is a first number of production. So let us push that first number production. So Q1 0, X is now 0, Z 0. So which production is pushed? Push the production, X gives 0. Now 0 is matching with 0. This 0 is matching with 0, therefore consume it. So Q1 input remaining is null, stack remaining is Z0, and we are now having, this is pop. Why pop? As I told, it is input is top of stack. Now Q1 null Z0, so it goes to Q2 null Z0. That is acceptance by final state. So this is acceptance by final state. All right. You can show this with the stack, and if it is asked to do instantaneous description, show instantaneous description, then what you have to do? So to show the instantaneous description, so I told you that you can show like this: delta, you are into Q0 state, input is your 100, stack is Z0. So now here, so it is going into Q1 state, that is Q1 state, remaining input is 100 and stack is XZ0. So that is going into Q1 state, 100, and stack is X is removed and its production is added, which is 1XX. So 1XX production is added, Z0. Okay, what it is doing here? It is doing push operation here. Push, X gives 1XX. So here, now 1 is matching with 1. So pop operation. So Q1, 1 is matching with this 1. So pop operation. Remaining input is 00. Remaining stack is XX, Z0. Here it is pop operation. Input is same as top of stack. Therefore pop operation. Now this is shown as Q1, 0 is not matching with stack. Therefore X is replaced by 0, X, Z0. So here it is a push operation again. Which push operation? X gives 0. This push operation is done. So that it is giving Q1. So now 0 is matching with this 0. Therefore consume it. So Q1 0. Remaining input is 0 and stack is XZ0. So here it is a pop operation because input is same as top of stack. Now 0 is not matching with X, so add its production. So Q1 0, X gives 0, Z0. So what we are doing here, push, X gives 0 production on stack. So that gives Q1 0 is consumed with this 0, so input is null, Z0. Okay, so here it is a pop because input is same as top of stack. And so that gives Q2 null, Z0. So this is acceptance by final state. So this is how you can do the instantaneous description also if it is asked. So if it is asked simulation, just simulation, then it is better to show with the instantaneous description because it requires less time and in just one line you can write it. But if it is specifically asked to show the stack operation, then you better write like this: state, input, stack, and then operation. Okay. Now what you do, you construct a PDA equivalent to following CFG. Now you try it. How many productions are there? See, let us see the first production S gives BD, first production. Second production S gives BC. Third production D gives SC. Fourth production C gives AA. Fifth production B gives 0. And last production, sixth one, A gives 1. So for all these productions, you have to write down the transitions. Okay. So all of you try it. I'll give you 5 minutes. Are you all trying?
Yes, sir.
Oh, yes, thank you. So how it will be? So you start in the initial state, that is Q0. That is a start state. So you go to the Q1 state by pushing the start symbol of the grammar. So which is a start symbol of grammar is S. So we have null as input, Z0 on stack. So we push S on stack. So S Z0. Now here in Q1 state, we will write the productions. So these will be all push productions. This will be all push productions. So all push productions we have to write it. So this, so when null is the input, S is on stack. Then we have to remove S from stack and add its production, which is BD. Similarly, for second production, when null is input, S is on stack. Then what we have to add its production, BC. When null is input, D is on stack. Then we have to remove D from stack and we have to add its production, which is SC. When null is input, C is on stack. Then we have to remove C from stack and add its production, which is AA. And when null is input, B is on stack, then we have to add its production, which is 0 on stack. And when null is input, A is on stack, we have to add 1 on stack. So that means all these productions, so these are push operations for productions. And these push operations are to be done when input is not equal to top of stack. Then we have to do push operation. Now we have to do a pop operation. So pop operation, how it is shown. So which are the terminal symbols? So terminal symbols are 0 and 1. So when 0 is input, 0 is on stack, then pop it. And when 1 is input, 1 is on stack, then pop it. So these are pop operations. And this is to be done when input is same as top of stack. And now we have to terminate. So how to terminate it? So when come to the final state, which is Q2, it is a final state. So when input is finished, that is null, Z0 on stack, then Z0 is kept as it is. So this is how you can design the PDA. And now how to do it? Now write 7 tuple of PDA. Now if it is actually asked for, if this problem is asked for more than 8 marks, let's say 8, 9 marks, then you must do all these things. But if it is asked for just for 4 marks or maybe up to 5 marks, then you draw this PDA, this much PDA, and then you can show its simulation. Okay, so write the 7 tuple of PDA. So, and then after that, show simulation, that is instantaneous description ID for input. So what will be the input for this? S gives BD. So 0. We can generate a string. So which string we can generate? So S gives BD. B gives 0. D gives, let's say, SC. So that 0, S gives BC, C, again B gives 0, C gives AA. So that gives 0, 0, 1, and finally A gives again AA, that is 1, 1. So let us simulate it for 0, 0, show simulation for 0, 0, 1, 1, 1 for this. So how will you do the show the simulation? So delta Q0 input is 0, 0, 1, 1, 1 and Z0 on stack. So that gives us, we are into Q1 state and starting symbol is pushed on stacks 0, 0, 1, 1, 1, S, Z0. So now here, since input is not matching, so 0 is not matching with S, therefore we have to do push operation. So that means Q1 0, 0, 1, 1, 1, and which production to be pushed onto stack so that we can get that string is S gives BD. So let us push that on stack. So S gives BD, so BD Z0. Now which production? Q1 0, 0, 1, 1, 1 and B gives 0. That production can be pushed onto stack. So B gives 0, D Z0. So here we have push operation. So which push operation we are doing? S gives BD. Here we are doing push operation. Which push operations we are doing? B gives 0. Now this 0 is matching with this 0, therefore consume it. So Q1 0, 1, 1, 1 and D Z0. So here we are doing pop because input is same as top of stack. Now again Q1 0 is not matching with D, therefore add its production. So D gives which production to be added? So D gives SC production can be added. So SC Z0. So here push. So which push operation? D gives SC. Now again S gives BD operation can be added. Q1 0, 1, 1, 1. S gives BD. BD. We are using BD or BC. No, we are using BC. Sorry. So here instead of BD, now which production to be pushed onto stack? BC. C Z0. So we are push S gives BC on stack. Now B gives 0 can be added now. So Q1 0, 1, 1. Here 0 CC Z0. So here we are push B gives 0 on stack. Now this 0 is matching with this 0. Therefore pop it. So that is Q1 1, 1 CC Z0. So here pop operation we are doing. Now C is not matching with that. Sorry, one more one. So this is now Q1 1, 1, 1. C is now converted as AA C Z0. So we are having push C gives AA. And then again Q1 1, 1, 1. A is converted as 1 A C Z0. So we are having push A gives 1. Now 1 is matched with 1, so that is Q1 1, 1. So this consume AC Z0. So it is pop operation. Now similarly Q1 1, 1. A is converted as 1. What it is happening? It is not matching. A. C is again. So what is C? C gives A or AA? C gives AA. So that's what it is. BC 0. C is AA. Yo. And one more C AA. So that means 0, 0, 1, 1. And again 0, B0, C is AA. and this C is A. So 4 ones has to be there. So one more one, one more one, 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 one. So C Z0. So now here it is push A gives 1. Now this 1 is matching, so that is Q1 1 1 C Z0. So it is pop operation. Now again C push operation. So Q1 1 1 AA Z0 push C gives AA, and then now finally Q1 1 1 A is 1A Z0 push A gives 1. Then this is Q1 1 is matching with this one, so consume it 1A Z0. So it is pop operation. Now so that gives Q1 null, sorry, 1 A is 1 Z0, that is push A gives 1, and 1 1 is matching, so that is Q1 null Z0. This is pop. And finally you are in Q1 state, null is input and Z0 on stack, so that comes to Q2 state, null Z0. So this is acceptance of string, which string? 0 and 4 ones. 0 1 2 3 4 by final state. All right, so this is how you have to do it. Now can you do it for this PDA? Draw PDA for CFG. S gives A as B, S gives AB or null, and simulate it for recognizing AAA double B. So how many productions are there? First production, S gives A as B. Second production, S gives A. Third production, S gives B. And last fourth production, S gives null. So for all these you have to do it. Okay, so I leave up to you now. As a homework, you complete this. So this is how we have completed the push down automata. There is one more problem again with the another grammar. It has come in exam for 8 marks. So I'll share this PDF to you. You try to solve these two remaining problems in your notebook. So this is how we have completed the push down automata unit. Tomorrow we will see the next unit, which is Turing machine. Turing machine is a advanced machine of the PDA. In PDA we have stack, external memory as stack. While as in Turing machine, we have a memory in which we can go forward, backward, anything. So that means it can work as last in, first out, or first in, first out, or anything. That means we can write in memory, input memory. So we will learn that Turing machine in the next lecture. Do you have any question?
No, sir.
समजलं का तुम्हाला सगळ्यांना आजचं लेक्चर समजलं? असं कोणी आहे की ज्याला नाही समजलंय? ओके, So what I'll do now, I'll share this PDF to you, and you can try solving these remaining problems. You will better understand this when you actually solve in your notebook. Okay. So thank you all of you for joining the session. So, so we'll stop here.